Today I wanted to talk, let's say, about what we developed in the last years for really simplifying fluorescence lifetime analysis. So I would like to jumpstart this presentation saying that why I basically founded FLIM Labs and why I started this company. Because at some point, I was doing my PhD. I had that experience also of a Master of Science in the US, and I found that there was basically a hole in the market because there were, let's say, no instrumentation specifically designed and dedicated for fluorescence lifetime assessment. So I had this idea in mind to create something really only meant for doing fluorescence lifetime analysis without the need of compromising into, let's say, other type of features. So my idea was to create something simple to access, simple to use, and with a bigger aim of democratizing fluorescence lifetime analysis. And the way for doing so was to create hardware and software solution optimized and designed to work together only for doing fluorescence lifetime analysis. So not only for doing, just saying, let's say general purpose time tagging or general purpose picosecond pulse lasers. I wanted to meant and to do something only for fluorescence lifetime analysis. And the idea was to implement, as I guess that Chiara told you about, time-correlated single photon counting techniques in which we excite our sample with a very short laser pulse, and then we analyze the decay profile of our fluorescence signal. For doing this, we basically need to have a TC-SPC electronics and a TC-SPC setup. And if we were, to dive into the bare minimum setup for accomplishing TC-SPC, we need a picosecond pulse laser, so a pulse laser. We need, of course, a sample. Here I am just throwing a cuvette. We need an emission filter because we need to separate the fluorescence from the laser light. And since we are doing single photon TC-SPC, we need a single photon detector. And then a third element is a electronics readout that allow us, to acquire single photons and then to reconstruct the decay profile of fluorescence. How we do so? We are basically delivering pulses to the sample and measuring the arrival time of photons in respect to the laser pulse. And then we basically hand this information out to a computer that will basically draw a histogram of all the arrival times of our photons, giving us the possibility of, reconstructing the intensity decay profile. So here you see I have a pulse laser. I have my fluorescence filter, my single photon detector, and acquisition electronics to allow me to do this measurement of arrival times. So with this type of principle and technique in mind, we developed what we call the FLIM starter kit. So a comprehensive solution made up by a pulse and laser source, TC-SPC electronics, so it's a time tagger, it's a TDC, it's a time to digital converter, single photon detectors, and everything, coupled with some softwares, which I'll tell you more about. The idea for the kit was to have picosecond pulse lasers, which are fiber coupled for allowing, let's say, maximum flexibility when dealing with optical setups. I'm talking about single point time resolve setups, but also imaging setup. And so we decided to design and engineer our lasers from scratch. And we ended up also having a USB powered version because we wanted only to provide, let's say, a laser with optimized specifications for dealing with fluorescence lifetime measurement. So we optimize the peak power, and we were optimizing also the full width of maximum. As you can see here, we can go as low as 50 picoseconds. And also we decided to give a USB power and USB control to the laser. Then this FLIM kit and the whole, let's say, instrumentation that we have for fluorescence lifetime analysis, also we offer And we developed two types of single photon avalanche dye detectors. These are single element detectors. One that has a peak sensitivity more in the red region of the spectra, so let's say 633 nanometer, and a second detector which is more blue shifted, so with a peak sensitivity at 450. So in these, having these two possibilities allow us really to explore all the visible range. And then, of course, last but not least, we developed our own time tagger, so our own data acquisition card to be able to measure the time of arrival of photon in respect to the laser pulse. And this card is very compact, is very lightweight, and most importantly is USB powered. We decided to have some type of specifications that were optimized for lifetime measurement, meaning that we did not want to have, let's say, 1 picosecond time beam resolution or 1 picosecond precision, because it's basically an overkill for fluorescence lifetime measurement. And this is, let's say, allow us also to optimize all the softwares that are provided with the data card. In fact, the data card can support 3 different types of software for doing single point analysis, and they are all Python based. Now, I can tell you a little bit about what we also are doing with this starter kit. We are the coordinator of LaserPlot, where we aim to develop early screening for pancreatic cancer. And the idea is to develop a liquid biopsy and to excite fluorescence out of this blood sample, and eventually be able to tell healthy patient from unhealthy patient. So this is the idea. And LaserPlot, I would say, is possible because we have this generation of instrumentation that is merely focused on fluorescence lifetime analysis and allow us, to pursue medtech type of applications. Coming back to, the imaging part of this talk and this presentation, we recently started to couple the FLIM starter kit to imaging setups. As you can see, we have our laser, the detector, the time tagger, but this time the optical setup we try to, to illustrate is a microscope. So we have our scanning system for performing laser scanning microscopy. And you see that if I provide my data acquisition card imaging synchronization signal, I am able basically to reconstruct a whole image. And so we started to use, let's say, the card in conjunction with a software that we recently developed, which is called FLIM Imager. I'm going to show you some screenshot, and then I'll show you a quick video on how the imager works. The idea is to have, let's say, a super simple graphic user interface with maybe just 2 or 3 buttons, and to already, let's say, use a very straightforward way to give the user some kind of result. Here you see the FLIM phaser approach being implemented. And then we also thought that when exporting the data out of the FLIM imager, it would be nice to have, let's say, a dedicated library for the data to be compatible with. So we teamed up with the PhaserPy team, and we were able to have this, library for reading our files and analyzing them using the PhaserPy library. Here I prepared a simple video. Okay. So the idea is that we export our data together with a Python script, and then we can run the Python script and import the PhaserPy library into our Python script. So basically, we can have our data visualized into Python, but also being processed using, let's say, the PhaserPy library. So you see here into the phaser plot, we applied 2 regions of interest, one blue and one red. So we were able to segment the image. It's a convallaria sample. Here, out of these 2, let's say, circlets, we take the centers, and we were trying to assess the different composition of the sample with two, let's say, compositions, so component A and component B, and we were also able, to derive a map of lifetimes either in the phase and in the modulation according to the phase plot approach. So after the video, oops, okay, so with this technology in mind, so with this technology in our hands, so the starter kit, the software, and this phase of pi library on our side, we went on and tried to, use the kit in combination with pre-existing setups. And so we started with a very old machine, so it's a Nikon A1R, and we gave, let's say, a second life to the Nikon A1 because we were able to couple directly part of our kit to the scanhead and to, let's say, perform FLIM phasor analysis. So here is our Nikon machine. This is the scanhead. You see it's written A1. We were coming into the scanhead with a yellow fiber, is a monomode fiber bringing the laser, and then this other fiber was going, you see, to this box under which we have the detector. So here is the laser going in, is the fluorescence going into our detector. Both the laser and the detector were connected to our data acquisition card for implementing TCSPC, and the data acquisition card was directly wired to the microscope controller for getting the pixel line and the frame clock for imaging reconstruction. Everything was, let's say, connected, of course, via USB to a computer. And then here you can see our imager doing the phasor plot analysis and segmenting, let's say, two populations within the same sample. Moving forward to the presentation. We also have experience with a barrier Steadicon. And here you'll see really the potentialities of our FLIM imager and the whole, let's say, kit. So the barrier Steadicon is nice because it already has all the signals that are needed for doing FLIM. So we just simply had to really hook up our data card in a plug and play manner and to run our software parallelly to the Steadicon. So here is what you would see in the Steadicon software. This is the same sample image in the Steadicon software and in the FLIM image. As you see, as I was saying before, the idea was to really give the user 2 or 3 buttons with all the rest of the parameters hidden or, let's say, already sorted out for doing, let's say, FLIM and doing FLIM phasors. You'll see that the image is really in real time. The phasors are also processed in a real-time manner, and the phasor cloud can be, let's say, segmented depending on the type of analysis that you want to achieve. Then, of course, we can also do some ROI type of analysis and get back to the main let's say, phasor plot. You see here, I'm continuing to show you, let's say, this duality of acquiring one image with the barrier software and then acquiring the very same image with our FLIM imager. Also, we actually, this is like the latest news. You may have heard about this OpenUC2 company. They are developing this open access little microscope, and the idea was to give really the FLIM power to this microscope. So we started to do the coupling of the starter kit with the microscope, and this is the very first image that we were able to acquire. It's a convallaria sample. But here you can see also the TCSPC decay profile of the convallaria. Last but not least, We also connected our FLIM kit with a Bruker Ultima 2-photon excitation microscope. The schematics a little bit more complex because we were able to use already the photomultipliers which are present on the Bruker together with a MITI Deep Sea 2-photon excitation laser source. We connected everything with our data acquisition card. We were able to sample the pixel line and frame clock coming from the Bruker control unit that allow us to reconstruct the image. And most importantly, given the 2-photon excitation, some, let's say, a good filter set, we were able to acquire NADH type of fluorescence, export the data via Python, and you see, this is my intensity image. This is the related phasor plot. I'm computing the FLIM image. Here is represented with the phase of the phasor plot analysis, and then transforming in this data, deriving a metabolic trajectory, as Chiara, I'm sure she explained before. Let's say, transforming the FLIM information into a metabolic information with a metabolic trajectory. So we were able to derive the metabolic index ratio between a glycolysis and oxidative phase, computing also an overall an average metabolic index. This, let's say, upgrade of the Bruker Ultima was possible thanks to the fact that together and in a parallel way to the FLIM starter kit, we also developed some accessories to make sure that the FLIM starter kit was compatible and is compatible with other lasers and other detectors. I'm gonna briefly tell you about the accessories. We have a constant fraction discriminator. We have just an amplifier for amplifying the signal of a PMT, for example. And also we introduce a splitter for splitting the signal, let's say, from a photomultiplier so that the user can still continue to use the pre-existent setup in a parallel way to the FLIM Labs setup. I would say, I mean, this is all for today. So thank you for the opportunity. And of course, I am willing to answer all your questions.